Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us somewhere both deeply familiar and endlessly strange, into the nature of time itself. We'll ask questions that have haunted physicists and philosophers alike, and we'll do it slowly, gently, like walking through a silent library of stars. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's begin. Time. It's one of those things you don't need to define to feel its presence. You can't hold it. You can't see it. You can't stop it. And yet, it shapes every part of your life. Every wrinkle on your skin, every ring in a tree, every crumbling stone on an ancient temple, all of it, touched by time. It's strange, isn't it? That something so invisible, something you can't bottle or weigh or put in your pocket, could have such power over everything that exists. And yet we speak of time like it's simple. We ask, what time is it? How long will it take? Do we have enough? But underneath those everyday questions lies a deeper one that doesn't have such a neat answer. What is time, really? Is it a flowing river, carrying us from birth to death like fallen leaves? Is it a ticking clock, keeping score of existence, or is it something else entirely? For most of human history, time was marked by natural rhythms, the sun rising and setting, the moon swelling and fading, the change of seasons, a heartbeat, a footstep, a breath. But as our minds grew curious and our tools more precise, we started to realize that time wasn't quite so cooperative. It stretched, it shrank, it refused to tick in lockstep across the universe. And in the 20th century, a quiet patent clerk in Switzerland cracked open the sky and rewrote everything we thought we knew. Einstein didn't just tweak the math, he shattered the entire picture. He showed us that time wasn't a backdrop, it was part of the stage itself. That time and space weren't separate threads but were woven together in a great invisible fabric called spacetime. And like any fabric, it could bend, it could stretch, it could ripple, and what bends it? Massachusetts energy. Even you, just sitting there breathing gently in your bed, are slightly curving the space-time around you. And when that fabric curves, time changes. Near something very heavy, like a black hole, time slows down. When you move very, very fast, close, to the speed of light, time slows for you compared to someone standing still. This isn't science fiction. This is science fact. GPS satellites orbiting above Earth have to account for time dilation from both their speed and their altitude, or else your phone would put you in the wrong place entirely. So already we've taken a tiny step into time travel, without building any machine, without jumping into a glowing portal, just by understanding how strange time really is. But the journey doesn't end there. What if we could do more than move forward a little slower? What if we could skip ahead, or turn around and walk back? What if we could see ancient empires rise and fall, talk to our past selves, or peek at the distant future of the universe? Is that just fantasy? Or could the laws of physics actually allow it? In the chapters ahead, we'll drift gently through all of it. The theories, the paradoxes, the quiet wonder of imagining a different relationship with time. We'll meet wormholes and warp drives, talk about clocks that run backwards, and learn why your memory might already be a tiny time machine. Don't worry if some of it sounds complicated at first. We'll take it slow, like mist curling through the branches of a quiet forest. Every idea will have time to stretch its legs and settle in beside you. Because that's the magic of nights like these. You don't need to be a physicist to feel the mystery. Just a curious traveller, floating on the current of a question. So take a deep breath. let the weight of the day fall away, and together, let's gently begin our journey through the tangled, beautiful, and profoundly strange fabric of time. You're probably used to thinking of time as something steady, predictable, a stream that flows in one direction, second after second, day after day. You wake up, eat breakfast, glance at the clock and carry on. Time ticks, clocks count, the sun sets, everything moves forward. But that quiet sense of certainty, that time is simply what the clock says, is one of the most delicate illusions your brain constructs. And physics doesn't see time that way at all. In the everyday world, we talk about now as if it's a shared experience. When you text a friend across the globe or sit beside someone and say, "Right now this is happening," it feels obvious that you're both living the same moment. But Einstein would gently disagree. According to the strange, elegant world of relativity, there is no single, universal now. Your now and someone else's could be separated not just by distance, but by time itself. And the faster you move, or the closer you are to something massive, the more that separation grows. This isn't a matter of poetic musing. It's baked into the fabric of the universe. You see, time and space are not two separate things. They are one, woven together into what we call spacetime, a four-dimensional fabric where your position in space and your position in time are inseparable. When you move through space, you also move through time. And when gravity acts upon you, it pulls not just your body, but your clock, subtly slowing the rhythm of your seconds, dragging time itself into a different pace. Imagine space-time as a soft, stretchable sheet. If you place something heavy in the middle, say a bowling ball, that fabric bends. And now, if you try to roll a marble across the sheet, it curves around the dip, pulled not by some invisible force, but by the shape of space and time itself. Gravity, then, is not a force pulling down, but the natural motion of things following the contours of curved space-time. But time isn't just affected by gravity, it's also warped by motion. The faster something moves, the slower time passes for it, relative to something standing still. This effect, known as time dilation, is not just theoretical. It has been measured with astonishing precision. When scientists fly atomic clocks on airplanes, or measure the behaviour of fast-moving particles like muons in cosmic rays, they see time stretch and bend just as predicted. And so, even though it feels like time is ticking at a universal rate, like some cosmic metronome tapping in the dark, the truth is far stranger. Your heartbeat may feel steady, but someone else's clock, moving at near the speed of light, would tick slower by comparison. On a mountain, where gravity is slightly weaker, time runs faster than at sea level. In deep space, far from stars and planets, time stretches out almost imperceptibly. These aren't science fiction ideas. They're facts confirmed again and again. Now pause for a moment and think about what that means. If time doesn't move at a fixed rate, if now is not the same for everyone, then what is time really? In physics, time is not a thing that flows. It's a dimension, like left or right, up or down. We don't ask, what makes space flow? Because space just is. It exists as a stage where events happen. And in the same way, time is part of the stage. It's not something that pours over us like water. It's the spacing between events, the structure that allows sequences to unfold. There is no river of time. There is only the map, the strange, curved, four-dimensional map that holds everything that ever happened and everything that ever will. This leads us to one of the most curious ideas in modern physics, that all of time might already exist, not just the past which you remember, not just the present which you experience, but the future too, which you haven't yet reached. Some physicists and philosophers call this the block universe. In this view, every moment, every kiss, every sneeze, every thunderstorm and falling leaf is already part of space-time, Just like every location exists in space, every moment exists in time. You're not moving through time. You're moving through slices of the block, like turning pages in a book that's already written. And yet, it doesn't feel that way. We don't experience time as static. We feel motion, change, memory, anticipation. We feel the now. That strange dissonance between experience and reality. That's part of what makes time so mysterious. It's not just a scientific question. It's a deeply personal one. The clock on the wall may agree with Einstein, but your mind still hears the ticking. You don't need to fully understand the equations of space-time to appreciate the beauty of this contradiction. That's what makes time such a perfect companion for nights like this. It's a presence we all know, and yet it slips away the moment we try to hold it still, like mist over a quiet field, or the fading impression of a dream as you wake. So if your sense of time ever feels unsteady, if a moment stretches longer than it should, or collapses too quickly, know that the universe is stranger than your watch, and that's okay. In the next chapter of our journey, we'll go deeper into this illusion. We'll explore why time might not really flow at all, and what that means for your memories, your tea going cold, and the curious way eggs always break but never unbreak. But for now, just rest in the wonder. Time isn't what you think it is, and maybe, just maybe, that's the most magical part. Close your eyes for a moment, unless you're already halfway there. Think about how time feels. It seems to move forward, doesn't it? A steady current that pulls you from one second to the next, like a gentle river. You wake up, the sky brightens, the coffee brews, and then evening arrives to tuck you back into bed. Day by day, season by season, year by year. It feels as though time flows, always forward, never backward. But what if that's not how the universe works at all? You see, physics doesn't actually demand that time flow. It doesn't even require a direction. The deepest laws of nature, the ones that govern how particles behave and how light moves and how matter changes, are time symmetric. That means they work just as well going forward as they do in reverse. In a purely mathematical sense, the universe doesn't seem to care if something happens or unhappens, if a glass shatters on the floor, or if it rises from the shards and reassembles in mid-air. Both directions are allowed by the equations, and yet, we never see that second one happen. Why? The answer, or at least the best one we have, lies in a quiet principle that governs everything from black holes to ice cubes: entropy. Entropy is a measure of disorder, of randomness, of how scrambled a system is. A room with books perfectly arranged by colour and size has low entropy. A room where they're scattered across the floor mixed with crumbs and crumpled papers has high entropy. And the second law of thermodynamics, one of the most trusted laws in all of science, tells us that in a closed system, entropy always increases. It's not that order is impossible, it's just vastly unlikely. If you drop an egg onto the kitchen floor, it splatters. That's easy. That's natural. That's entropy doing what it does. But if the molecules in that puddle of yolk and shell were to spontaneously leap back together and reform into a perfect egg, that would be an extraordinary reversal. Not impossible according to physics, but unimaginably improbable. Like flipping a coin and getting heads 1 trillion times in a row. And so, because the universe is always trending toward disorder, we feel the passage of time as movement from order to chaos, from low entropy to high. A cold drink warms up, a hot cup of tea cools, you grow older, you forget. All of these are entropy at work, quietly, invisibly, shifting the balance toward a more probable state. This, scientists believe, is the source of the arrow of time. It's not that time itself has a built-in direction. It's that our universe began in an incredibly low entropy state, smooth, structured, and strangely simple. Over time, it's become more disordered, more complex, more jumbled. And in doing so, it gave rise to a kind of one-way street. We remember the past because it was more ordered. We don't remember the future because it hasn't happened yet, or more precisely because entropy hasn't had time to increase there. It's a humbling thought, isn't it? That the reason you feel time move is not because it's flowing like water, but because the universe is slowly unravelling step by step into all the ways it could possibly be. And yet, here's where it gets even stranger. There's a view of the cosmos, supported by some physicists and philosophers, that says time doesn't really move at all. That everything, every moment, already exists. This is the idea we touched on before, known as the block universe. In this model, the universe isn't like a movie being played, frame by frame. It's like the entire reel is already printed. Every frame, every moment, every heartbeat and raindrop and goodbye. And you, drifting through what feels like the present, are just experiencing one slice at a time. Not because the movie is moving, but because you are. In this way of thinking, the past hasn't vanished, and the future isn't waiting to be created. They're all there, already part of the tapestry. It's not so much a river as it is a frozen landscape, and your mind is like a warm light moving across it, one moment at a time. Of course, this isn't how we experience the world. To you, right now, the past feels fixed, the future feels uncertain, and the present feels, well, present. But perhaps that's just what it feels like to be a human inside time. From outside the frame, if such a viewpoint were even possible, time might look very different. Quiet, still, complete. Some thinkers have even proposed that what we call the flow of time is a mental construct, that your brain, in processing events and memories, creates the illusion of motion, like a flipbook or an old film reel, where each image is still, but together they appear to move. Your consciousness becomes the projector, lighting up one frame after another, never aware that the film is already fully drawn. It's a gentle paradox, that time might be static, but still feel dynamic, that the universe doesn't move forward, but we do. So what are we to make of this? Well, you don't need to answer that tonight. In fact, you don't need to answer it at all. That's the beauty of exploring a mystery like time. It's not about solving it. It's about sitting with it, letting it unfold in your imagination like soft waves on a midnight lake, letting yourself drift between science and wonder, between clocks and stardust. Because sometimes the most peaceful thought isn't that time moves forward, it's that everything you've ever been and everything you'll ever be is already there, held quietly in the shape of the universe. And maybe that's enough. You don't need to understand quantum equations to feel time. You carry its traces with you every day, folded gently into the lines on your hands, the fading of a childhood memory, or the soft familiarity of a path you've walked before. Time touches everything, but perhaps nowhere more delicately than inside your mind. We often think of time as something outside us. It's the ticking of a clock, the changing light through your window, the number in the corner of your phone screen, but that's only part of the story, because your brain, quietly and constantly, is also a time machine. Not the kind made of gears and glowing circuits, but one built from memory, imagination and perception, from billions of neurons whispering to each other in patterns you can't quite hear. Right now, as you listen to this, you're not living in the present exactly, not completely. There's a small delay, a microscopic lag, between the world around you and your awareness of it. When sound reaches your ears or light touches your eyes, it takes time, just a fraction of a second, for your brain to register it. And then it takes a little more time to assemble it into something coherent. Your mind is constantly stitching reality together slightly after it happens. So the now you're experiencing is actually already a memory. Recent, yes, but not truly present. This might sound unsettling, but it's not a flaw. It's how consciousness works. In fact, it's necessary. Because everything your brain does, from recognizing faces to recalling names to deciding whether you're hungry, depends on patterns, on comparisons, on context, and context requires time. That's where memory comes in. Memory isn't just a file cabinet of past events. It's the glue that binds your moments into a life. Without memory, there is no story. Without story, there's no sense of movement. Without movement, there's no time. Imagine waking up with no recollection of yesterday. You'd still perceive the world around you, the ticking clock, the rustling breeze, but it wouldn't mean anything. There'd be no before to compare it to, no thread to follow. Each second would be an island, and you'd be a traveller lost between them. Memory is what allows time to exist inside your mind, but memory is only one direction on the map. Your brain also travels forward, not physically of course, but through imagination. You picture tomorrow's breakfast, next year's vacation, a conversation that hasn't happened yet. This isn't a coincidence. The parts of your brain responsible for remembering the past are also deeply involved in simulating the future. You use the same mental structures, the same regions of your hippocampus and prefrontal cortex, to recall as you do to predict. That's why dreams can feel so confusing. They jumble time, mix memory and imagination, shuffle people and places like cards. In dreams, you may meet a version of yourself from childhood, or sit in a room that hasn't existed yet, or relive something almost exactly, but with just enough change to make it feel unfamiliar. Your brain, unburdened by daylight logic, wanders through time like a sleepy traveller, curious, disoriented, and oddly content. Even when you're awake, you do this more than you think. You replay conversations in your head. You imagine outcomes. You relive arguments. You rehearse reunions. Sometimes the event hasn't happened yet. Sometimes it never will. But to your brain, the distinction is blurry. Real and imagined time are close neighbours, separated only by a thin veil of awareness. And then there's déjà vu. That odd sensation that you've lived this moment before. It's not time travel, not in the literal sense, but it's a glimpse into the way your brain handles repetition and familiarity. It suggests that time, even within your mind, isn't always linear. It loops, it echoes, it glitches. So here you are, not just moving through time, but creating it, weaving it from the threads of memory and hope, stitching it into a personal tapestry that no one else sees in quite the same way. That's part of what makes time so hard to define, because it's not just a physical dimension, it's also a mental landscape, one shaped by emotion, shaped by meaning, shaped by what you choose to remember and what you don't. There are moments that stretch, like the silence before bad news or the joy of a slow morning in bed, and there are moments that vanish, entire hours spent scrolling, blinking, wondering where the time went, and yet all of them are real, all of them are time, not in the way a physicist would chart on a graph, but in the way your heart recognizes them, as significant, as fleeting, as something you felt pass through you like wind through a curtain. As we prepare to return to physics in the next part of our journey, it's worth pausing here, gently, to recognize something quietly profound. That your experience of time is not wrong, just incomplete. The clock might be objective, but your life isn't measured in seconds. It's measured in memories, in changes, in soft transitions from who you were to who you are becoming. And that is its own kind of time travel. You've already visited 1,000 versions of yourself, and you will visit 1,000 more, not with a machine, but with thought, reflection, and the quiet miracle of being conscious. So as you rest now, let your mind drift where it wants to go. Forward, backward, sideways, to childhood afternoons or imagined futures, to what was and what never quite was. You are, after all, the only time traveller who knows exactly how your story feels from the inside. and that makes your journey through time unlike any other in the universe. Let's imagine a quiet morning. You and your twin, identical in every way, born just moments apart, are sitting together, sipping warm drinks, watching the sky shift from blue to gold. For all the years of your life, you've aged in sync. Wrinkles appear together, hair greys together, birthdays celebrated on the same day with the same cake. But now, your twin makes a strange decision. They climb aboard a spacecraft, sleek, humming, prepared to travel near the speed of light, and promise to return someday. You stay behind, years pass. For you, they pass slowly but steadily. The days blend into one another like ink on wet paper. You walk through seasons, through cities, through memories. Eventually the spacecraft returns. You hurry to meet your twin, heart pounding with anticipation, and when you see them, they haven't changed. Not really. A few days older, maybe a week. You, on the other hand, have aged decades. This is not fantasy. This is time dilation, a real consequence of Einstein's special theory of relativity, and it has been confirmed again and again by experiment. The faster you move through space, the slower time passes for you, relative to someone standing still. Strange to think about, but it's not hard to understand if you picture time and space as being part of the same fabric. When you move faster through space, you move slower through time. It's as if the universe has a kind of balance, a conservation of motion between the where and the when. The faster you go, the more your personal clock slows down compared to someone watching you. But this isn't something you'd feel. To the traveller, everything feels perfectly normal. Their heart beats at the usual pace. Their tea cools at the usual rate. It's only when they return and compare clocks that the difference becomes apparent. This idea, while once radical, has become deeply accepted in modern physics. In fact, we've measured it. One of the most compelling examples comes not from distant spacecraft, but from tiny particles called muons. These particles are created high in Earth's atmosphere when cosmic rays collide with molecules in the air. Muons decay very quickly. They're fleeting things, lasting only millionths of a second. In theory, they shouldn't be able to reach the ground. There just isn't enough time for them to survive the journey. And yet, we detect them at sea level. Why? Because they're moving so fast, close to the speed of light, that time slows down for them. Their internal clock from our point of view ticks more slowly, and so, from their perspective, the ground reaches them quickly. From our perspective, their decay is delayed. Both are true. This isn't illusion, it's reality, split gently by perspective. Physicists have also flown atomic clocks on high-speed aircraft, comparing them with identical clocks left on the ground. The airborne clocks tick slightly slower, just as relativity predicts. Not only that, but our GPS satellites orbiting Earth must account for both the speed at which they move and the weaker gravity they experience. Without these corrections, tiny as they may seem, your phone would put you dozens of meters off from your true location. So every time you check a map or navigate to a cafe, you are depending on the strange truth of time dilation. Even astronauts, our closest approximation of high-speed travelers, have lived this in tiny but measurable ways. Sergei Krikalev, one of the longest-serving cosmonauts in history, has spent more than 800 days in orbit. Thanks to the speed of the International Space Station, he has technically skipped ahead in time by a fraction of a second. It's not enough to notice, not enough to dodge a bill or arrive late to dinner, but it's real. Krikalev is, in a very literal sense, a few milliseconds younger than if he'd stayed on Earth. The numbers are small now because our technology is still slow compared to the universe's speed limits. But the principle is vast. If you could build a spaceship that moved at 99.999% the speed of light, and you travelled in it for what felt like a few months, centuries could pass on Earth. In theory, you could leave in the year 2025 and arrive back home in the year 3025, while still young and healthy. You'd have skipped through centuries, not by stepping into a portal, but by simply moving very, very fast. Time travel to the future, then, is not only possible, it's already happening. Tiny, slow, humble steps, but steps nonetheless. The universe doesn't forbid it. It whispers it, quietly, in the motion of particles and the drifting of clocks. The future is reachable, not by magic, but by velocity. There's a soft poetry in this, isn't there? That the faster you go, the more gently time cradles you. That speed is not just motion, it's also a kind of cushion, a stretching of seconds, a quiet resistance to the aging that grips everything else. It makes you wonder, in a universe where time bends and stretches like fabric, where the future is waiting, quietly, patiently, what does it really mean to move forward? We'll continue this thought in the next session, when we step into a different kind of slowing. Not one caused by speed, but by gravity. Because while motion can pull you toward the future, gravity can sink you into it. And near the heaviest objects in the universe, time all but stops. But for now, rest with this simple truth. You are already a time traveller, just by existing, just by moving, just by breathing. The future is always coming, one step or one stretch at a time. Close your eyes and imagine standing at the edge of something massive, not just large, but unimaginably dense. A star that has collapsed into a sphere only a few kilometers wide, so heavy that it bends light, pulls on space, and even slows down time itself. This isn't science fiction. It's the quiet truth of gravity in the language of general relativity. Einstein's theory of general relativity told us something extraordinary, that gravity is not a force pulling you downward, like a string tugging on a puppet, but rather the curvature of space-time itself. In this picture, mass tells space-time how to curve, and curved space-time tells matter how to move. But this bending doesn't just affect where objects go, it changes how time flows. Near something massive, whether a mountain, a planet, or a collapsed star, time ticks more slowly. Not because the clock is broken, but because the very fabric of time is stretched. If you could place two clocks side by side, one at sea level and one on a mountaintop, and watch them long enough, you'd find the higher clock ticks just a little faster. It's a subtle difference, barely noticeable, but real. And as you move closer to stronger gravitational fields, the difference becomes profound. Let's take a gentle walk through an example. Imagine you and a friend are communicating across a great distance. You remain safely on Earth, while your friend drifts ever closer to a neutron star, one of the densest known objects in the universe. From your point of view, as they approach that crushing gravity, their clock appears to slow down. Their voice, if transmitted, stretches, becomes deeper, more drawn out. Their heart still beats, they still blink, but to you, everything they do takes longer. And from their point of view, nothing feels different. Time for them seems normal. It's only when you compare notes that the strangeness reveals itself. Take this thought even further, to the edge of a black hole, a place where gravity is so intense that time, from the perspective of an outside observer, nearly freezes. This is not poetic exaggeration. From your position far away, you would see your friend approach the event horizon, that invisible boundary beyond which nothing returns, and slow down more and more until their movements become glacial, then imperceptible. From your frame of reference, they never truly cross the threshold. They just fade into stillness. But for the person falling in, time continues normally. They would pass the horizon in what feels like seconds. What lies beyond remains a mystery, but what's clear is that time is not the same for both of you, not even close. The weight of gravity has stretched time, pressing it into strange shapes, like soft dough pushed into the corners of a pan. This bending of time is not limited to the distant universe. It happens here too, just in smaller doses. Atomic clocks, so precise they can lose or gain just a fraction of a second over millions of years, have been used to measure these differences. In one famous experiment, scientists placed one clock at the bottom of a building and another at the top. After a long enough period, the clocks disagreed, slightly, subtly but undeniably. Time ran faster higher up, where the pull of Earth's gravity was slightly weaker. It's a strange thing to realise. The top of your head is aging just a tiny bit faster than your feet. This isn't just academic curiosity. It has real-world consequences. The GPS satellites that circle our planet move fast enough and float high enough that their clocks experience both time dilation from their speed and gravitational time stretching from being further from Earth's mass. Engineers must constantly adjust for these effects. Without those adjustments, your navigation app would become wildly inaccurate in a matter of minutes. So every time you get directions to a coffee shop or find your way home, you're relying, quietly, invisibly, on Einstein's insight that gravity bends time. This concept was brought vividly to life in the film Interstellar, where astronauts visit a planet orbiting close to a supermassive black hole. Because of the intense gravity, 1 hour on the planet equals 7 years on Earth. Though dramatized, the physics behind it is accurate. That kind of time dilation could, in theory, exist in our universe, if you were willing to get close enough to something unimaginably heavy, and come back out again. Of course, there are risks. Approaching a black hole too closely doesn't just slow time, it stretches space. The gravitational difference between your head and your feet could become so extreme that you'd be torn apart, a process scientists rather colourfully call spaghettification. It's a dramatic name for a very quiet death. But set aside the danger for a moment. Think about what this all implies. Time is not fixed. It is not equal. It is not constant. It flows differently depending on where you are, how fast you're going, and what's around you. And in the presence of gravity, the same gentle force that pulls your teacup to the floor and keeps your feet grounded, time itself bends like light through water. There is something deeply calming about that, isn't there? To know that time is not a rigid master, but a flexible fabric. That, depending on where you rest your head, your dreams may stretch a little longer, that every moment, even when shared, might pass a little differently for each of us. We're not all moving through the same clock. We never were. So as you drift into stillness tonight, imagine yourself floating in space, not just moving through it, but inside a river of time that bends and slows and stretches around the stars. Gravity is not a trap, it's a rhythm, a slow celestial breath. And when you let go, even just in your imagination, the future begins to reveal itself, one curved second at a time. Imagine a sheet of paper, smooth and wide, like the empty canvas of space. On one side of the sheet you draw a small star. On the far side you draw a second star. The distance between them is vast, maybe hundreds of light years. Now fold the paper gently so that the two stars touch and pierce a hole through both points with a pencil. Suddenly, what once took lifetimes to cross can now be reached in a single step. This simple image, often used in science classrooms and popular films, is a powerful metaphor for something far more mysterious: the wormhole. In the language of physics, a wormhole is a hypothetical tunnel through the fabric of space-time, a bridge connecting two distant regions, perhaps even two different times. Unlike ordinary travel, which takes you along the surface of the universe, wormholes cut through it, offering shortcuts not through space, but through the geometry beneath space itself. The idea isn't new. In fact, it has its roots in Einstein's own work. In 1935, Albert Einstein and physicist Nathan Rosen proposed what came to be known as the Einstein-Rosen bridge, a mathematical solution to Einstein's equations that suggested two black holes could be connected by a kind of tunnel. They didn't call it a wormhole, and they weren't suggesting spaceships could travel through it. At the time, it was more of a curiosity, a mathematical oddity in the equations of general relativity. But the idea stuck. Over the decades, physicists and dreamers alike kept asking, what if this bridge could be real? What if it could stay open long enough for something or someone to pass through? That brings us to a name you may have heard before, Kip Thorne. A Nobel Prize-winning physicist and one of the scientific minds behind the film Interstellar, Thorne helped take the concept of wormholes from a mathematical curiosity to a scientifically rigorous, if still entirely hypothetical, possibility. In the late 1980s, Thorne and his colleagues asked a deceptively simple question. Could a wormhole exist that was traversable? In other words, could you enter one end, pass safely through, and emerge somewhere else without being crushed, vaporized, or lost? To their surprise, the answer wasn't no. It was maybe, but you'd need something very strange to hold it open. That something is known as exotic matter. Exotic matter isn't some magical substance from another dimension. In physics, the word exotic simply means something that behaves differently than the ordinary matter we're used to. The kind that makes up your body, your pillow, the stars overhead. Exotic matter in this case would need to have negative energy density, meaning it would push space apart instead of pulling it together. And that pushing is crucial. A wormhole, if it exists, would naturally want to pinch closed. Just like a tunnel collapsing under the weight of Earth above it, the curved space-time would try to seal the hole. Exotic matter could provide the outward pressure needed to hold the tunnel open, to keep the walls from falling in. Of course, we've never found exotic matter in large quantities. We don't know how to make it, or store it, or arrange it into the fantastical shapes wormholes require. But physics, as we understand it, doesn't strictly forbid it. And in the deep, shimmering realm of quantum field theory there are hints, little whispers, that such strange energy might not be pure fantasy. So where would such a wormhole go? It could connect two regions of space, two planets, two galaxies, two corners of the universe separated by incomprehensible distances. But the equations allow for something even more wondrous. If the two ends of a wormhole experience different rates of time, perhaps due to motion or gravity, then the wormhole could connect not just space, but time. Enter one end and you could step into the future, or perhaps the past. It's important to pause here, in the quiet, and acknowledge something. None of this is confirmed. No wormholes have ever been observed. No exotic tunnels have lit up our telescopes or sent signals through space. This is theoretical physics, a realm of thought experiments, rigorous equations, and dreams that might never leave the chalkboard. And yet, there's beauty in the idea. A beauty that lingers, like the shape of a dream you can't quite remember. The universe, as we uncover it, seems more and more like a place that might allow such pathways. Not easily, not without difficulty, but not impossibly either. The laws of general relativity, those silent rules written into the structure of the cosmos, permit wormholes to exist. Whether the rest of physics, quantum fields, energy constraints, cosmic causality agrees is another question. But for now, in this moment, we're allowed to imagine. Imagine stepping through a doorway and arriving on the other side of the galaxy. Imagine returning to a childhood moment, not as a ghost, but as a visitor. Imagine sending a message not just across space, but across time. A quiet hello to someone long gone, or not yet, born. That's what wormholes offer. Not certainty, but possibility. In the next part of our journey, we'll gently explore how a wormhole, if manipulated just right, could become something even stranger, a time machine. But for now, let's sit with this idea, that the universe might be threaded with invisible bridges, curved paths through space-time, waiting only for the right balance of physics and imagination to reveal them. And if we ever find one, it may not just lead elsewhere, it may lead elsewhen. Let's imagine, for a moment, that someone has handed you a wormhole, a stable one, held open by just the right balance of physics and strangeness, curved space and negative energy. You stand before it like you might stand at the entrance of a tunnel cut through the side of a mountain. On the other side, not another place, but another time. It sounds like fantasy, but if the equations of general relativity are to be believed, if the mathematics that govern the curvature of space-time continue to hold, then this scenario, as peculiar as it may seem, isn't impossible. The key lies not just in having a wormhole, but in what you do with it. Picture this. You keep one end of the wormhole here, on Earth. You anchor it, maybe in a quiet room, under soft lighting, next to a ticking clock. And then you take the other end, and you begin a journey. You accelerate it to a significant fraction of the speed of light. Perhaps you sling it around a black hole, or take it on a cosmic voyage, then bring it gently back to its twin. To an observer, both ends now sit side by side, seemingly unchanged. But their clocks tell a different story. Because of time dilation, the travelling end of the wormhole has experienced less time than the stationary one, maybe hours less, maybe years, maybe centuries. And so now you have a peculiar situation, a tunnel in space-time where one end is in the present and the other is in the past. If you step through from the present-day mouth, you'll emerge days or years earlier. If you walk the tunnel the other way, you leap into the future. This isn't magic, it's geometry. The wormhole connects 2 points in space-time, and if those points are no longer synchronized in time, then the tunnel itself has become a time machine. There's a name for this kind of path through space-time. It's called a closed time-like curve, or CTC. It's time-like because it follows the rules of time-based motion. You're not teleporting, you're moving in a continuous way. It's closed because the path loops back on itself. And it's a curve because space-time is curved, not just in space, but in time as well. A CTC allows, in theory, an object to return to its own past, to loop around through the fabric of the universe and arrive at a moment it has already lived. The idea is mesmerizing and deeply unsettling, because once you allow time travel into the past, you open the door to paradox. What happens if you step through a wormhole into the past and accidentally prevent your own journey from ever occurring? What if you alter the past so that the future you came from no longer exists? This is the heart of the causality problem, the tangled question of what happens when cause and effect become circular. Physicists have wrestled with this idea for decades. Some suggest that the universe might self-correct, that paradoxical actions are simply not allowed. Others propose that many worlds' interpretations might apply, that each timeline change branches into a separate universe, avoiding contradiction by creating an entirely new history. And some suggest that nature itself might prevent wormholes from being used this way, that subtle quantum effects or instabilities would destroy the tunnel before any paradox could take place. And that brings us to another problem: stability. Even if you could construct a wormhole and move its mouth to create a time difference, you'd still need to keep it open. And keeping a wormhole open against the crushing weight of gravity, against the natural collapse of space, requires exotic matter with negative energy density. We spoke of this in the last session, but here the requirement becomes even more extreme. To maintain a traversable wormhole that allows time travel, the exotic matter would need to be shaped precisely, balanced perfectly, and placed exactly right. A shift too far in one direction, a small ripple in energy, and the tunnel might collapse, not gently, but catastrophically. Some physicists have suggested that trying to turn a wormhole into a time machine might destabilize it so quickly that it closes before anything meaningful can pass through. Others speculate that the laws of physics might include some hidden rule, as yet undiscovered, that forbids time machines outright. Something like a universal veto. You may fold space, you may warp time, but you may not rewrite the past. And yet, there is no such rule written clearly in the mathematics. The equations, as they currently stand, allow time loops. They don't require them, but they don't forbid them either. It leaves us in a curious place, standing at the edge of theoretical possibility, looking into a foggy landscape where physics, philosophy and logic begin to blur. A place where causality isn't a straight line, but a spiral, where events might influence their own beginnings, where the past is not behind us, but beside us, just waiting for the right doorway to be opened. As we drift deeper into this speculative realm, it's important to remember we are still grounded in the rules of general relativity. This is not pure fantasy. It is, at worst, a thought experiment, and at best a glimpse of what may someday be possible, if not by us, then by some far future civilization, patient enough and curious enough to weave their ships through the folds of time itself. But, even if such machines are never built, the idea alone invites reflection on how we understand change, on how we think about choice, on whether our memories are fixed or flexible, and on whether time in the deepest sense is something we move through, or something we shape, one thought at a time. So, for now, close your eyes and imagine a quiet room, a doorway humming with possibility, and a path that doesn't lead elsewhere, but elsewhen. The word exotic tends to conjure up images of faraway places, unfamiliar spices, strange birds in thick forests, or fruits with names that roll awkwardly off the tongue. But in physics, exotic doesn't mean something colourful or rare in the traditional sense. It means something unlike anything we've ever touched. Something that behaves in a way that ordinary matter simply doesn't, and perhaps can't. If wormholes are to become more than just elegant equations or curious metaphors, if they are to be opened, walked through and kept from collapsing, then exotic matter is the key. Not just to hold them open, but to allow time itself to stretch, bend and loop in ways that feel more like stories than science. Let's take a step back and ask, what would such exotic matter actually be? To answer that, we need to visit one of the strangest ideas in theoretical physics, negative energy. Now, energy is something we all understand on some level. You eat food and your body has energy. You plug in your phone and it charges. The sun pours energy across the sky, warming your skin and stirring the air. Energy feels positive, always building, moving, feeding the systems around it. But in the quantum world, the world of fields and probabilities and restless particles, energy doesn't always play by the rules we expect. In certain situations, under extremely specific conditions, quantum fields can produce regions where energy is, quite literally, less than zero. One of the clearest examples of this is the Casimir effect. Imagine two parallel metal plates placed a tiny distance apart, not even wide enough for a virus to slip through. In the vacuum between them, quantum fields still fluctuate. Normally these fluctuations produce virtual particles, popping in and out of existence, jittering like sparks that exert pressure in all directions. But between the plates, only certain wavelengths can fit. The result is that there's less quantum energy between the plates than outside them, and so the plates gently attract each other. This difference in energy density, this subtle imbalance in the froth of quantum nothingness, is a hint of negative energy. It's not dramatic. It won't suck in planets or create time loops on your kitchen table. But it proves, experimentally, that the fabric of space can be bent in ways that lower its energy below what we'd expect from nothing at all. That's not quite the exotic matter we need to hold a wormhole open, but it's evidence that negative energy exists and that the universe allows it under certain conditions. The challenge is that such effects are tiny, incredibly small. The Casimir effect can only be measured with extremely sensitive instruments, and even then, it's not something we can scale up or bottle or shape into a shimmering tunnel through space-time, but it suggests something vital, that exotic matter isn't impossible, just elusive. In order to stabilize a wormhole, to keep it from collapsing under the immense gravitational forces trying to close it, you would need a region of space where energy is not only negative, but arranged precisely to counteract the curvature of the tunnel. That means engineering matter and energy into forms we've never seen. Fields that push rather than pull. Structures that resist collapse not by being strong, but by being strange. Some physicists suggest that such matter could emerge from the vacuum itself, not as a stable substance, but as a quantum fluctuation, a kind of temporary scaffold made of geometry and possibility. Others speculate that advanced civilizations, if they exist, might have found ways to manipulate quantum fields to produce negative energy on demand, a kind of space-time engineering we can barely begin to imagine. But for now, exotic matter remains a placeholder in our equations, a requirement that floats in the margins of possibility. It doesn't break the laws of physics, but it certainly presses against their boundaries. This is where general relativity and quantum mechanics begin to disagree. Not loudly, but awkwardly. General relativity describes space-time as smooth and continuous, like an endless rubber sheet. But quantum mechanics describes the universe as jittery, pixelated, flickering with uncertainty. And when you try to combine them to understand how gravity behaves at the tiniest scales, you get mathematical confusion, divergences, singularities, answers that stretch toward infinity and never return. To build a stable wormhole, or to truly understand the nature of time travel, we may need a theory that unifies these two great pillars of physics, something beyond Einstein, beyond Schrödinger, a theory of quantum gravity, still incomplete, still out of reach. Until then, exotic matter is both a mystery and a promise, a ghostly suggestion that the universe is not yet finished revealing itself, that there may be materials we haven't seen, energies we haven't tapped, geometries we haven't walked, that the fabric of reality is more flexible than we once believed, and that with the right kind of insight, the impossible might just become unlikely. There is something deeply peaceful in that uncertainty, because it means the story isn't over. The answers haven't all been written. The wormholes, if they exist, are still waiting, not just in distant galaxies or hidden labs, but in the quiet spaces between ideas. So tonight, as you rest, consider that the universe may be woven with threads we don't yet understand. That somewhere between the ticking of clocks and the shimmering of particles lies a kind of energy not yet touched by human hands. And that maybe, just maybe, time itself is waiting for us to discover how to hold it open. Imagine sitting still, not moving at all. The stars outside your window shimmer in place. The ship you're on makes no sound, no rumble, no shuddering push of engines. It feels like floating in stillness. And yet, in the span of a single breath, entire solar systems slip past. Galaxies become distant blurs. Time warps, space folds, and you, cradled inside this motionless vessel, are moving faster than light. Except, you're not moving at all. Space is moving around you. This is the quiet dream of the Alcubierre drive, a theoretical concept proposed in 1994 by Mexican physicist Miguel Alcubierre. Inspired by the equations of general relativity, and as legend has it, by a certain sci-fi series involving starships, Alcubierre imagined a way to travel faster than light without breaking any physical laws, at least not directly. You see, according to Einstein's special relativity, no object can move through space faster than light. As you accelerate toward light speed, your mass increases, your energy demands skyrocket, and eventually, the universe itself seems to say, no further. But Alcubierre's idea was clever. What if, instead of moving through space, you moved space itself? In his proposed model, a spaceship would sit inside a kind of warp bubble, a region of flat space-time surrounded by curved space-time. In front of the bubble, space would contract, Behind it, space would expand. The result? The bubble itself, and everything inside it, would ride along a wave of distorted space-time, like a surfer on a cosmic tide. To an outside observer, the bubble might move faster than light. But locally, inside the bubble, nothing violates relativity. The ship remains stationary relative to the space around it. There's no acceleration, no speed limit broken because the ship isn't moving through space-time. It's being carried by it. It's an elegant idea. A loophole, if you like, though in physics we call such things solutions. The mathematics works, at least on paper. Alcubierre's equations showed that such a bubble was consistent with Einstein's field equations, which govern how mass and energy shape the curvature of space-time. He even modelled how such a bubble might start and stop, compressing space in front of it and releasing it behind like a spring. But here's where the dream begins to shimmer and blur. For the warp drive to function, it would require negative energy density, the same exotic matter we discussed in the wormhole sessions. In fact, the energy requirements are even more extreme. Some early estimates suggested you'd need the mass energy of the entire observable universe just to push a small ship. Later refinements lowered this number, but even the most optimistic calculations still require an amount of energy far beyond anything we can produce. And it's not just the quantity of energy, it's the kind. You'd need a form of exotic matter that repels space rather than attracting it. Something capable of creating the outward push needed to bend space into that unusual bubble shape. So far, no such material has been found, and its very existence remains uncertain. Then there are the instability issues. Some physicists have pointed out that such a warp bubble, if created, might be inherently unstable. Tiny fluctuations, the kind that naturally arise in quantum fields, could cause the bubble to collapse or unravel. Worse, as the bubble accelerates, it might collect Hawking radiation at its leading edge. Intense, high-energy particles that build up like a bow wave and then release in a deadly burst when the ship stops. A kind of gamma-ray explosion that could sterilize anything nearby. And yet, for all these problems, the idea hasn't been disproven. In fact, researchers at NASA's Eagleworks laboratory and other institutions have continued to explore warp bubbles, not with full spaceships, but with tiny fluctuations in electromagnetic fields that might mimic some of the drive's properties on a microscopic scale. Whether this leads anywhere practical is still unknown, but it shows that physicists are willing to play in this sandbox, not because they expect to launch warp ships next year, but because understanding the edge of what's possible always teaches us something. There's a subtle beauty in the Alcubierre drive, even if it never becomes real, because it reminds us that space isn't empty. It's a fabric, a shape, a thing that can stretch and bend and ripple. The universe isn't a static box, but a living geometry. And if we can find the right way to shape that geometry, even the most distant stars might become reachable, not by flying to them, but by bringing them closer. It also whispers something profound about our relationship to motion and stillness. That perhaps speed isn't always about thrust and force. That perhaps, in the far reaches of physics, the fastest way to move might be to remain perfectly still, while the universe shifts softly around you. As you let this idea settle, consider the silence of such a voyage. No engines roaring, no air rushing past, just the hum of curved space-time gently lifting you from one corner of the cosmos to another. A journey not through distance, but through geometry. A bubble of calm inside a storm of impossible motion. We may never ride such a wave, but in the equations of Einstein, in the thought experiments of dreamers, and in the soft hush of midnight curiosity, the possibility remains. And maybe that's enough for tonight. If black holes are the universe's great devourers, swallowing stars, light, and even time itself, then what, you might ask, is their opposite? Imagine something that doesn't pull matter in but pushes it out. Not a drain, but a fountain. Not an endpoint, but a beginning. In the theoretical mirror of general relativity, such an object exists. It's called a white hole. While black holes mark the places where space-time bends so steeply that nothing escapes, white holes are mathematical curiosities that do the reverse. They can't be entered, and instead expel everything outward. Nothing can fall in, nothing can remain inside. In this sense, they're time-reversed versions of black holes. White holes first appeared in the same equations that predict black holes, suggesting that if you can have one extreme, a point of no return, then perhaps the mirror image is also possible. But while black holes have become cornerstones of modern astrophysics, confirmed through gravitational waves and X-ray observations, white holes remain hypothetical, beautiful, balanced, and possibly forbidden by the practical unfolding of the universe. Still, they invite strange questions. Could a black hole in one region of space connect to a white hole somewhere else, like a tunnel through space-time? Some versions of the Einstein-Rosen bridge, the early model of wormholes, suggested exactly that. That perhaps what enters a black hole might emerge from a white hole, not annihilated but transformed, perhaps not even destroyed at all. Of course, real black holes don't seem to behave that way. Their interiors, according to current understanding, contain a singularity, a point where density becomes infinite, and our laws of physics falter. If white holes do exist, they may require unknown physics, or perhaps they are remnants of the very early universe, flickering into being and vanishing just as quickly. From these grand cosmic fountains, let's turn to something even stranger, a particle that may never have existed, but still lives in the minds of physicists, the tachyon. A tachyon, if real, would be a particle that always travels faster than light. Unlike photons or electrons or anything with mass, tachyons would move so quickly that they could never slow down to light speed, just as we can never speed up to it. They would exist forever beyond the cosmic speed limit, slipping through time in reverse, rewriting cause and effect as they go. And that's where the trouble begins, because tachyons, according to the rules of relativity, would bring paradoxes. They could, in theory, transmit information into the past. A message sent with a tachyon might arrive before it was sent, undoing its own cause. This kind of logical loop, where effect precedes cause, breaks the tidy chain of time that underpins science as we know it. That's why most physicists believe tachyons are mathematical artifacts, solutions that appear in certain equations but don't correspond to physical reality ghosts, you might say, haunting the corners of theory but never observed, never detected, never quite real. Still, like white holes, they persist, not as confirmed objects, but as reminders that our universe may allow for concepts that seem impossible, not because they are true, but because they help define the edges of what is. And yet, faster-than-light events do occur in another context, not in cosmic fountains or ghostly particles, but in the quantum world, where rules bend and uncertainty reigns. In this realm, particles can do something called quantum tunneling. Picture a tiny ball rolling toward a hill. In classical physics, if the ball doesn't have enough energy to climb the hill, it rolls back. Simple, predictable. But in quantum mechanics, there's a small chance, just a whisper of a probability, that the ball appears on the other side of the hill without ever going over the top. It's as if, instead of rolling over the barrier, it simply slips through it. This isn't magic, it's quantum behavior, and it's been observed in countless experiments, in radioactive decay, in the inner workings of transistors, even in biological enzymes. Tunneling isn't fast in the traditional sense, but it happens in a way that seems instantaneous, a kind of probabilistic jump, not bound by the same timelines we use to measure motion through space. Some interpretations suggest this might involve superluminal behavior, speeds faster than light, though no information is transmitted this way, and no causality is broken. But it hints at a truth we've returned to again and again, that time and speed are not absolute. They bend, flicker, and vanish in the places where quantum mechanics whispers its quiet rules. So here we are, standing among strange possibilities, a universe with tunnels that stretch space, particles that dance faster than time, holes that give instead of taking, and behaviours that seem to mock our sense of cause and effect. And yet, none of these are wild fantasies. They're ideas shaped by mathematics, tested by experiment, and discussed by minds that spend their lives peering into the nature of reality. It's easy to get lost in the spectacle, but the wonder isn't just in whether white holes or tachyons or warp drives are real. It's in the fact that we can ask these questions at all, that we live in a universe rich enough, strange enough, structured enough to even consider such things. That behind the stars and particles there is a geometry of wonder, curved and folded and full of quiet secrets. So tonight, as you drift towards sleep, imagine a sky filled with not just light, but possibility. Fountains of stars, ripples of space, and somewhere, in the soft edges of time, something going faster than you ever thought it could. Not to escape, but to return. Picture time not as a straight line, stretching endlessly in one direction, but as a soft spiral, a thread gently curving back on itself. A ribbon floating in water, folding through space in loops so smooth and seamless, you can't quite see where the beginning ends, or where the end begins again. This isn't just a poetic image. It's a possibility allowed, however reluctantly, by the mathematics of general relativity. According to Einstein's equations, space-time is flexible, like a living fabric. It can stretch, ripple, and twist. And under certain extreme conditions, it can twist so far that the path ahead begins to curve around and lead back to the past. Physicists call these strange trajectories closed time-like curves, or CTCs. Closed because they loop. Time-like because they still obey the rules of moving forward in time. From your own point of view, you're always going forward. But the path you're on bends so far around space-time that eventually you find yourself back where you started, not just in space, but in time. You might expect that such curves are impossible, that something in the laws of physics would slam the door shut on such a wild idea. But oddly enough, general relativity permits them. The math works. The solutions exist. They're not necessarily practical, but they are allowed. One of the most intriguing examples of this possibility is the Tipler cylinder, named after physicist Frank J. Tipler. Imagine an infinitely long, incredibly dense cylinder, something with the mass of a star but spun so fast that its rotation drags space-time around it, like a spoon swirling honey in a jar. If you move close enough to the cylinder and follow a very specific path around it, the twisting of space-time could carry you along a loop, back into your own past. The key is frame dragging, the idea that rotating mass pulls space-time with it. A subtle but measurable effect confirmed by real-world experiments, like Gravity Probe B. Near something as massive and fast-spinning as the Tipler cylinder, that frame-dragging effect would be so extreme that time itself begins to warp. Of course, there's a problem. The cylinder has to be infinitely long, not just big, but literally without end, and made of ultra-dense material. And even a single photon or stray particle entering the system could destabilize the entire loop, preventing the curve from closing. In other words, it's mathematically possible, but physically unlikely. Another example comes from the brilliant mathematician and logician Kurt Gödel, who applied Einstein's equations to an entire rotating universe. In his model, the entire cosmos spins gently but persistently, twisting time into loops on a cosmic scale. In such a universe, you could, in theory, travel far enough in the right direction and return not just to where you began, but when you began. Gödel's universe was an elegant solution to the equations, but it doesn't match what we observe. Our universe appears to be expanding, not rotating, and we see no signs of the global frame dragging that his model would require. Still, the fact that Einstein's equations allow such a solution was unsettling even to Einstein himself, who seemed uneasy about the implications. These models, the Tipler cylinder, Gödel's universe, are like shimmering doorways in the fabric of space-time. Not open, not reachable, but possible, at least in theory. They invite us to consider time not as a strict progression from past to present to future, but as something more fluid. Something that, under the right circumstances, might fold. It's important to note that none of these scenarios have been observed. No one has seen a Tipler cylinder. The universe does not appear to rotate as Gödel imagined. And yet, the fact that they are not forbidden speaks volumes. Time, it seems, is more flexible than we were taught to believe. It is not just the ticking of clocks or the falling of sand through an hourglass. It is geometry, malleable, influenced by mass, motion and momentum, and in some corners of that geometry loops may form. Quiet, subtle ones. As you think about these possibilities, it may help to picture time as a garden path, one that occasionally doubles back on itself, curling between hedges you didn't notice were connected. You walk forward, always forward, and yet somehow you arrive where you began. Not by turning around, but by walking straight through a space that is curved. That is the dream and the caution of closed time-like curves. A universe where time does not just stretch into the future, but folds softly into its own past. A place where memories and possibilities walk the same road, quietly passing each other in the fog. Whether these loops exist anywhere in reality remains an open question. But in the pages of physics, in the equations of Einstein, and the imaginations of those who followed, they are as real as any possibility, a soft spiral in the fabric of time waiting only to be found. Now that we've opened the door to the past, however gently, we must pause, not to marvel, but to think. Because the moment you allow travel backward in time, you encounter something far stranger than wormholes or warp drives. You encounter the tangled loops of logic, the quiet puzzles of cause and effect, the soft but unyielding paradoxes that sit patiently in the folds of time waiting to be asked. The most famous of these is the grandfather paradox. Imagine, if you will, that you step through a time machine, a tunnel, a cylinder, a ripple, and find yourself decades earlier. You walk among your family, younger and unaware, and then, in a moment of mistaken action, or perhaps intentional interference, you prevent your grandfather from ever meeting your grandmother. The result is clear. Your parent is never born, which means you are never born, which means you were never there to interfere in the first place. It's a clean paradox, elegant in its contradiction, like a sentence that erases itself as you read it. This idea has puzzled physicists and philosophers alike, not because it's likely, but because it's logical, or rather, illogical in a way that challenges the structure of reason itself. If time travel to the past is possible, then causality, the chain of events that gives the universe its order, begins to unravel. The grandfather paradox is personal, but its cousins are just as haunting. There's the bootstrap paradox, where something exists without origin. A scientist finds a notebook on their doorstep detailing how to build a time machine. They follow the instructions, succeed, and later travel back in time to drop off the same notebook. So where did the notebook come from? It was never written. It loops endlessly between past and future, orphaned from any point of creation. Or imagine a world where someone travels back in time and gives a young Beethoven a collection of his own symphonies. The young composer studies them, memorizes them, performs them, and in time becomes the great Beethoven, whose symphonies were never his to begin with. This kind of paradox is named after a concept in science fiction, a bootstrap, a loop where the effect is its own cause, a thing that creates itself, a melody with no composer, a story with no author. There's also the predestination paradox. Unlike the previous two, this one doesn't involve contradiction, but inevitability. In this version, a person goes back in time to prevent a tragedy, only to discover that their very attempt causes the event they were trying to stop. Their interference becomes the trigger, their warning becomes the prophecy, and the future they tried to avoid becomes the one they helped create. It's not that the past resists change, it's that the change was always part of the story. Science fiction is full of such loops. In 12 Monkeys, a man's mission to prevent a pandemic leads directly to the moment he was trying to stop. In Arrival, a linguist learns a language that rewires her brain to perceive time non-linearly, and in doing so sees her own future as part of her present. In Interstellar, a man who falls into a black hole becomes the ghost from his daughter's childhood, not changing the past but fulfilling it. These stories linger in our minds not just because they are clever, but because they feel true in a deeper emotional sense. We've all had moments when our attempts to avoid something only bring it closer. We've all experienced echoes that feel like they came from the future, a memory you didn't know you had, a choice that feels already made, a dream that predicts a thing you didn't understand until afterward. Paradoxes in time travel are often treated like puzzles to be solved, as if the universe were a logic riddle and we only need to find the flaw. But perhaps they are not mistakes. Perhaps they are reflections of something we don't yet understand. They may be signposts pointing to the limits of our current models, or they may be warnings, gentle ones, that the past is not a place to be visited lightly. Physicists approach these paradoxes with caution. Some argue that the laws of nature simply do not allow them, that something would intervene before the contradiction could be completed. Others propose that the paradoxes are real, but resolvable, through alternate timelines, or quantum branching, or other frameworks we'll explore soon. But before we seek those solutions, it's worth sitting for a while with the discomfort, because these paradoxes, beyond their logic, remind us of something very human, the tension between fate and choice. If you could go back and change something, would you? If you did, would that change undo you? And if the change was already part of the past, did you ever have a choice at all? These questions may not have answers, but they form the quiet heart of every time travel story. Not the machines or the theories, but the longing. The longing to undo a mistake, to understand a moment, to reach into the past and touch something we lost. Perhaps time travel is less about physics and more about memory. And perhaps deep down the paradox is not that we might change the past, but that we can never let it go. When we open the door to the past, even just a crack, the light that spills through is tangled, beautiful but dangerous. With it comes all the delicate contradictions, the aching loops of logic, the paradoxes we explored just a moment ago. And so, we find ourselves asking not just whether time travel is possible, but whether the universe, in its quiet, unfolding elegance, might prevent it. This is the essence of a provocative idea proposed by Stephen Hawking, called the chronology protection conjecture. Hawking, known for his sharp wit and deep clarity of thought, once speculated that the laws of physics may contain hidden safeguards, not posted on signposts or announced by thunderclaps, but embedded deep in the mathematics, that prevent closed time-like curves, wormhole travel to the past, or any mechanism that could cause a paradox. In other words, the universe might have its own immune system, a built-in resistance to the confusion of time loops. The conjecture isn't a formal law or a proven theorem, it's a warning wrapped in mathematics. Hawking pointed out that many theoretical models that allow time travel to the past, whether they involve wormholes, rotating cylinders, or quantum tricks, seem to become unstable when you try to actually use them. They generate infinite energy, tear themselves apart under quantum feedback, or collapse under their own contradictions. It's as if reality itself says, "No, not this way." He famously joked that the absence of time travellers from the future was evidence enough that time machines don't work. But beneath the humour was a serious question. What mechanism protects causality? What keeps the past from being rewritten? One possible answer comes from quantum mechanics, and in particular the concept of decoherence. In quantum theory, particles can exist in multiple states at once, superpositions, until they are measured or interacted with. But in larger systems, these delicate superpositions tend to collapse. They lose their quantum behavior and choose a state. This process, called decoherence, is why you don't see tables in multiple places at once, or people who are both here and not here. The quantum possibilities decohere into a single classical reality. Some theorists suggest that this same principle might apply to time travel, that any attempt to create a paradox to loop cause and effect would be disrupted at the quantum level. Decoherence would collapse the contradictory path before it can complete. The paradox never finishes because quantum uncertainty won't let it stabilize. Another possibility, more speculative but deeply intriguing, is that paradoxes are resolved not by preventing the time traveller, but by branching the universe. This is the realm of the many worlds interpretation of quantum mechanics. According to this view, every possible outcome of a quantum event actually occurs, but in a separate parallel universe. The universe splits, quietly and without notice, at every fork in the road. Flip a coin, and there's a reality where it lands heads, and one where it lands tails. They both exist. You only experience one. Applied to time travel, this means that if you go back and change something, prevent your grandparents from meeting, say, you don't erase your own existence. Instead, you create a new branch, a new timeline where that action plays out. The original timeline continues unchanged. No paradox occurs because cause and effect still hold within each branch. From your point of view, you've altered the past, but from the universe's point of view, you've simply stepped sideways into another version of events. It's a comforting idea in some ways, a universe without contradiction, a place where all choices are possible, even the ones we undo, but it also invites a kind of quiet melancholy. If every choice creates a new world, then we are forever surrounded by ghosts of the paths not taken, echoes of lives we didn't live, moments we didn't choose, and yet, perhaps this too is a kind of chronology protection. Not a wall, but a garden. Not a warning, but a branching path. Some physicists argue that these branches are just metaphors, tools to help us think about probabilities. Others believe they are real as your heartbeat or the turning earth, just inaccessible to us. But either way, they offer a way to keep causality intact, even as we twist and stretch time into unfamiliar shapes. So then, can physics protect the timeline? Maybe. Perhaps through the laws of quantum uncertainty. Perhaps through feedback, loops that destabilize time machines before they can operate. Perhaps through infinite branches, each one carrying its own unbroken chain of events. Or perhaps through something we haven't discovered yet. A principle still waiting beneath the equations, quietly ensuring that time, though strange, remains whole. In the end, what we're left with is a kind of gentle paradox itself. The more we try to break time, the more we uncover rules that protect it. The deeper we go into the possibility of changing the past, the more we find that the past may already be unchangeable, or else already changed, quietly and without contradiction. And that, in its own way, is reassuring. It means the story we are living, the one we wake into and walk through and remember, has a shape. Not rigid but resilient, not linear but complete. So let the past rest, let it be what it was. Let the present unfold, and let the future remain unwritten, not because it must be, but because it can be. Let's imagine for a moment that you could walk into a laboratory, not a gleaming, noisy place filled with whirring machines, but a quiet one, dimly lit, serene, like a cathedral of thought. Here, time isn't measured by ticking clocks or glowing screens, but by slow breaths and equations gently unfolding like petals. In this room, we aren't simply theorizing about time, we're sketching it, carefully, delicately, as if it were something that might bruise under too much pressure. And at the centre of this sketch is a simple question. If we could build a time machine, not in fiction but in physics, what would it look like? First, we'd need something with the power to bend time, not in metaphor but in geometry. Something so massive, so dense and so dynamic that it can twist the fabric of space-time into spirals and loops. One candidate already exists in our universe, a rotating black hole, also known as a Kerr black hole. Unlike the simpler black holes that form from collapsed stars, those that pull inward in all directions equally, a Kerr black hole spins, and when it spins, it drags space-time along with it. This phenomenon is called frame dragging, and it's been observed in our own solar system in much smaller contexts, like Earth's gravitational field. But near a spinning black hole, frame dragging becomes extreme. Time and space themselves are pulled into a vortex. Near the event horizon of such a black hole lies a region called the ergosphere, where space and time swirl so strongly that even light must rotate with it. Some physicists believe that inside, or perhaps just outside this region, the geometry of space-time could allow for closed time-like curves. In other words, paths through space that eventually loop back in time. But a black hole alone won't be enough. We need structure. We need design. Enter the idea of a massive spinning ring, inspired by the tippler cylinder we discussed earlier. Instead of an infinite cylinder which is not physically realistic, imagine a colossal ring, a loop of ultra-dense material spinning rapidly in space. Inside the ring, frame dragging might be used to create a region where time bends back on itself. This ring wouldn't stand alone. It would encircle something even stranger, a traversable wormhole, its mouth held open by exotic matter, a material with negative energy density. The wormhole would serve as a bridge between 2 points in space-time. One end would remain near the spinning ring, immersed in the time-warped field. The other would be taken far away, perhaps at near light speed, to create a time difference between the two ends. Once stabilized, the wormhole would connect two different moments in time. You could enter one mouth in the future, step through, and emerge from the other in the past. The order of entry and exit wouldn't be determined by clocks, but by the warped space-time geometry between the two. But to navigate such a machine, to target a specific year, day, or hour, you'd need more than levers and buttons. You'd need something that could sense the subtle structure of space-time itself. Here's where the quantum world lends its strange hand once again. Some have speculated that quantum entanglement, that spooky, instantaneous link between particles across any distance, could be used as a kind of space-time GPS. Entangled particles could help synchronize time between the two ends of the wormhole. They wouldn't transmit information faster than light, but they might allow precise alignment of reference frames, ensuring that when you step through, you emerge at just the right moment. Of course, there would be risks, immense ones, even if such a structure could be stabilized, and that is a towering if. Tiny fluctuations in energy could destabilize the entire field. Vacuum decay might occur, collapsing space-time itself in a flash of radiation. The machine could generate feedback loops, paradoxes, or tears in causality that no equation can yet predict. And even if it worked, there would be the question of precision. Time is not a map with clear borders. It's not enough to say, "Take me to July 12th, 1955. You'd need to correct for relativistic drift, gravitational influences, planetary motion, solar activity, factors that might push you off course not by hours, but by centuries. And how do you test such a thing? You can't send a camera through a paradox. Still, in this quiet room of thought, we let the design unfold. A rotating black hole, whispering to spacetime with its momentum, a spinning ring, forging curves in time with sheer velocity, a wormhole bridged with exotic matter, humming in impossible equilibrium, and a quantum compass, delicate and silent, tracing the shadows of history. Not a machine made of gears and pistons, but of mass and motion, light and mathematics. Not something you drive, but something you become part of. A structure you enter not with certainty, but with faith in the equations that cradle you. Would such a machine ever be built? Almost certainly not soon, and perhaps not ever. The energy requirements are staggering. The exotic matter remains hypothetical, and the consequences of using it could ripple beyond comprehension. But the purpose of imagining it isn't necessarily to construct it. It's to understand what it would require, what kind of universe would allow it, what kind of beings could even attempt such a thing, and what kind of minds could dream it. Sometimes the value of a blueprint lies not in the machine it might one day build, but in the way it changes the ones who drew it. And so, for now, we sketch quietly. We fold our diagrams and place them gently back in the drawer, not discarded, not dismissed, just waiting, in case the future arrives before we expect it. There is another way to travel to the future, not by folding space, twisting time, or venturing through wormholes, but by waiting. Not the kind of waiting that passes with ticking clocks and calendar pages. Not the kind you feel while standing in line or lying awake before dawn. This is a stiller kind of waiting, a pause so deep that even time itself seems to forget you. This is the promise, quiet, strange and controversial, of cryonics. Cryonics is the idea that a human body, upon death, or just before it, could be cooled to such an extreme degree that all biological processes would slow to a near-complete stop. Metabolism, decay, cell activity, everything quieted. Not dead, perhaps, but not alive either. Suspended, and then, someday, reanimated. It sounds like science fiction, and for now it still mostly is. But the principle is rooted in something that already happens all around us. In seeds that lie dormant for decades before sprouting. In frogs that survive being frozen in Arctic ice, their hearts still, their breath paused. In tardigrades, microscopic creatures that can dry out completely, enter a state called cryptobiosis, and wake again when water returns, as if no time had passed at all. Even in human medicine, we see echoes of this idea. In certain surgical procedures, hypothermia is induced, deliberately lowering a patient's body temperature to slow brain metabolism, buying precious minutes during heart or brain operations. The body cools and time, at least in a biological sense, slows with it. Cryonics pushes this concept further, much further. The goal is not just to cool the body, but to preserve it at liquid nitrogen temperatures, around negative 196 degrees Celsius. At that temperature, water in the body would freeze, so a chemical process called vitrification is used instead. It replaces the water inside cells with a glass-like substance, avoiding the ice crystals that would otherwise shred cell membranes from the inside. If done correctly, and that is a very big if, the result is a human body in stasis. No heartbeat, no thought, no awareness, but also no decay. Preserved, like a message in a bottle, waiting to be opened by a future that knows how to read it. And this, in a way, is a kind of time travel. The person does not experience the passage of decades or centuries. They simply fall asleep, deeply, fully and without dreams, and then someday perhaps awaken into a world that has changed, a world where diseases that were once fatal are now trivial, where technology has advanced beyond recognition, where time, which once seemed to have taken everything, has quietly returned what it borrowed. But the challenges are immense. Cryonics today is not reversible. No human has ever been revived from such a state. The vitrification process itself can cause damage, especially at the molecular level. And even if the body were perfectly preserved, reviving it would require medical capabilities we don't yet possess. Ways to repair tissue at the cellular or even atomic scale, to restart complex systems that have been silent for decades. There are also ethical and philosophical questions. What does it mean to pause a life? What kind of future would one awaken into? And would you belong there? Would your memories remain intact? Would your identity endure the crossing? And who decides when, or if, you are revived? Despite these uncertainties, cryonics continues. Around the world, a small number of individuals have already undergone the process, or have made arrangements to do so. Some have chosen to preserve only their brains, hoping that one day the mind alone might be revived and placed into a new body, or even into a digital form. It's not mainstream science, but it is a serious pursuit, with real research, real facilities, and real hope. There's something deeply human in it, the idea that, instead of chasing the future with engines and equations, we might simply wait for it to arrive, that we might trust time not as an enemy to outrun but as a caretaker, that if we become very quiet, very still, and very patient, time might carry us forward like a gentle stream. In nature, this happens all the time. Seeds lie buried in the soil for years, waiting for the right warmth to bloom. Insects encase themselves in cocoons, letting the seasons pass around them. Even certain fish eggs can dry out, be blown across deserts in the wind, and hatch when they land in water again. If they can wait, why not us? Of course, this is not the same as the cinematic freeze chambers of science fiction. There are no blinking lights or hissing doors, just deep, cold, quiet storage and a bet, placed gently but boldly on the ingenuity of future generations. Cryonics is not yet a time machine, but it is a thoughtful pause, a scientific lullaby, a hope that sleep, in its deepest form, can be more than rest, that it can be passage. And maybe that's what makes it so compelling, because in the end, all of us are travelling through time, whether we run, drift, or freeze in place. The journey continues. And sometimes the most astonishing act isn't acceleration or bending the laws of physics. Sometimes it's simply choosing to wait. Why do we dream of time travel? Not just in science, but in stories, in whispers, in quiet longings that visit us when the world goes still. The idea appears again and again in films, books, bedtime tales, daydreams. It follows us like a shadow through culture and consciousness, not because we expect it to be real, necessarily, but because it touches something tender in us, something buried deep in our experience of being human. We are, after all, creatures of time. We live forward, but we remember backward. Our very identity is stitched together from memory. Who we were, who we became, and who we thought we might become but never did. Our lives unfold not as data, but as stories. And stories are made of time, beginnings, middles, endings. The idea of moving through time differently is not just scientific curiosity. It is personal, intimate, emotional. Time travel allows us to visit the unchangeable, to return to the moment when a loved one laughed for the last time, to fix the thing we regret saying, to pause the happiest hour of a summer afternoon just before it passed. It's not always about curiosity. Sometimes it's about healing. Sometimes it's about longing. And sometimes it's about asking whether the people we used to be still live somewhere inside the past, waiting to be remembered. Think about the stories we tell. From Charles Dickens's A Christmas Carol to Back to the Future, from Doctor Who to The Time Traveller's Wife. Time travel isn't just a narrative gimmick, it's a framework for exploring memory, identity, change. These tales let us ask impossible questions. If I met my past self, would I recognise them? Would they recognise me? If I glimpsed my future self, would I feel pride or fear? These stories echo because they reflect a truth we all feel but can't always express. That time isn't just something we pass through, it's something that passes through us. And in that passing, it leaves shapes. Sometimes those shapes are soft, a scent that brings you back, a dream that feels like a memory, a song that places you in a version of yourself you thought you'd forgotten. Other times they're sharp, a decision you can't undo, a person you can't call, a goodbye that didn't feel like one at the time. In this way, regret becomes a kind of time machine. So does nostalgia. So does hope. These emotions are not distractions from science. They are responses to time itself. They are how we navigate it, how we honour it, how we try, in our own quiet ways, to reshape what cannot be reshaped. And then there are dreams. Dreams are perhaps the closest we come to personal time travel. In them, we are unbound. Past and present blend. The dead return. The future speaks. Time folds, loops, dances without logic. We meet. Younger versions of people we know. We encounter our older selves. We watch scenes that never happened unfold beside ones that did. And in that dreamlike space, we find something strange. We don't question it. The impossible feels ordinary. Not because it is, but because our minds are already wired to move through time in more ways than one. The brain, after all, is a prediction engine. It constantly simulates the future, rehearsing conversations, anticipating outcomes. It also constantly reviews the past, replaying, reframing, remembering. Even when we're awake, we're always somewhere between what was and what might be. Time travel, then, is not so foreign. We already live in its shadows. Every time you reflect on your childhood, you're pulling the past into the present. Every time you imagine retirement, you're sending your thoughts into a future that hasn't yet unfolded. Every time you pause to wonder what life might have been like if you'd turned left instead of right, you're visiting an alternate timeline, not in body, but in thought. And maybe that's enough. Maybe the reason time travel appears in every culture isn't because we believe it will happen, but because it already does, inside us. Maybe it's not about machines or wormholes or paradoxes. Maybe it's about memory and imagination, regret and hope, dreams and daydreams. Maybe it's about trying to understand who we are, by remembering who we were and imagining who we could become. And in that sense, time travel is not a distant frontier. It's the soft terrain we walk every day, in silence, with every heartbeat. Because to be human is to carry time inside you, to wear the past like a coat with hidden pockets, to trace the future like a map you're not yet ready to unfold, and to live, not just in the moment, but across moments, layered, luminous, always reaching forward, always looking back. So perhaps the question is not whether we can travel in time. Perhaps the real question is, how do we make peace with the journey we're already on? Even if we never build a time machine, even if no wormhole ever stabilizes long enough to carry a traveller, even if we never fold space, stretch moments, or step into a glowing portal that opens onto the past or the future, there's still something deeply valuable about thinking about time travel. Because imagining the impossible doesn't just satisfy curiosity, it changes us. It shapes the kinds of questions we're able to ask. It expands what we believe is worth knowing. Wonder, after all, is not just decoration, it's a compass. The history of science is full of things that began as dreams, heavier than air flight, the bending of light, communication across oceans, the idea that the earth moves at all. Each was once unthinkable, laughed at, labelled absurd, until someone somewhere asked a question too strange to be practical, and then spent a lifetime trying to answer it. Time. Travel sits at the far edge of that tradition, the misty horizon where science brushes against poetry, where imagination dares to walk barefoot in equations. And while the math may be incomplete and the technology out of reach, the act of trying to understand it is already a kind of forward motion. Even now, thinking about time travel nudges real science forward. It leads us deeper into the nature of space-time, gravity, and quantum entanglement. It invites new questions about entropy, causality, and information. It encourages experiments that sharpen our understanding of the universe, not in fantastical leaps, but in tiny, careful steps. And it keeps us humble. Because when you study time, truly study it, you start to see how small we are, how short our window of awareness. You realise that even our best clocks are mere approximations, our years an arbitrary carving of something vast and fluid. Time becomes not just a measurement, but a mystery. Not just a flow, but a structure we barely understand. Wonder opens the door to that mystery. It's why children ask about time machines before they ask about thermodynamics. It's why science fiction often plants the first seed of a future scientist's curiosity. It's why some of the most advanced physics questions being explored today, from loop quantum gravity to the nature of the Big Bang, trace their lineage back to someone somewhere wondering, what if time doesn't work the way we think it does? And this wonder doesn't belong only to scientists. It belongs to storytellers, philosophers, dreamers, to you, listening in the dark, to every person who has looked at an old photograph and felt a sudden ache, to everyone who has watched the stars and imagined not just distance but duration. The light from a galaxy not only shows us where it is, but when it was. The night sky is a mosaic of lost moments. In that sense, every star is already a kind of time machine. We don't need to go anywhere, we only need to look up. And in another sense, we don't need time machines because we already live inside one. Earth itself is a vessel moving through time. You're older now than you were at the start of this sentence. The planet is spinning, orbiting, changing. The sun is aging. The atoms in your body have already travelled. Through stars, through oceans, through ancestors. Time is not something you enter, it's something you carry. So when we imagine stepping into a portal, punching in a year, and vanishing into light, it's not always about escape. Often, it's about continuity. The desire to feel connected across eras, to leave a message for the future, to know that we mattered even briefly in the story of time. And here's the quiet miracle: you already do. Your existence is already a bridge. Your thoughts ripple forward. Your memories reach back. You are a node in the web of time, woven between ancestors and descendants, between forgotten whispers and unborn songs. The very act of imagining time travel is already time travel in a way. It's a movement of the mind across possibilities. It's a form of resistance to the idea that now is all we'll ever have. It's a way of saying that the past isn't lost, and the future isn't sealed, and the present is not the whole story. So keep imagining, keep wondering, even if no machine ever hums to life in your garage. Even if the only wormholes you travel are in books and dreams and quiet what-ifs, because wonder is not wasted. It stretches the mind, yes, but it also stretches the heart, and the future, whatever it becomes, needs that. It needs people who ask bold questions, who walk to the edge of the known and linger there listening, who are not content with answers but enchanted by the shape of the next question. The future needs engineers and poets, physicists and daydreamers, children who press their ears to clocks and ask what's inside. Because humans, strange and fragile as we are, have a habit, a beautiful, improbable, sometimes reckless habit, of doing impossible things given enough time. Now that we've travelled so far, through black holes and wormholes, equations and paradoxes, dreams and diagrams, it's time to slow down, to stop trying to chase time or catch it in our hands, to stop asking whether it's flowing, looping, or frozen. Because here, at the edge of this long journey, we can finally rest with a different thought. That maybe time isn't something we pass through at all. Maybe time is something we're inside of. It's easy to picture time as something falling, a river pulling us forward, always faster, always away from what was. But that's not the only image. There's another way to feel it, and it begins not with falling, but with floating. Imagine for a moment that you're adrift, not sinking, not rising, just gently suspended, as if time were a deep, warm ocean and you, a soft speck in its current. No destination, no beginning or end, just the quiet sensation of being carried, not rushed, not judged, just held. That's what time becomes when we stop measuring it, when we stop assigning it to clocks and calendars, when we stop turning it into deadlines and regrets. In those rare, beautiful moments, the hush of a morning before the world stirs, the calm between waking and sleep, the stillness after a deep breath, time loses its sharp edges. It becomes a kind of background hum, a steady presence, not a countdown, a cradle. And it's in that cradle that we begin to understand something gentle and true, that we're not outside of time trying to conquer it. We're woven into it. Every heartbeat is a clock, every memory a marker, every plan, every hope, every scar, every dream, a note in time's quiet song. From the atoms in your cells to the stars in the sky, you're stitched into the same fabric. The calcium in your bones was forged in the heart of a dying star. The breath you just took might have once passed through the lungs of someone long gone. The world around you, the air, the light, the sound of your own thoughts. It's all part of this slow, unfolding rhythm. You're not behind time. You're not ahead of it. You are within it. And that means rest is not resistance. Sleep is not defeat. It's part of the journey. There's no need to outrun the years or rewrite what's been written. There's no need to imagine a perfect moment in the past or a glittering rescue in the future. You're already here. You made it. Right now. Right here. In this gentle moment that asks nothing of you except presence. So if your thoughts begin to drift, let them. If you start to forget where this all began, or what we were talking about, that's fine too. Let the words soften. Let the concepts blur. Let your body grow heavy, like a stone placed gently into still water. There's nothing more you need to do, nothing more you need to solve. You've thought enough for one night. This journey wasn't about building a time machine. It wasn't about solving physics or proving anything to anyone. It was about being here, with the wonder, with the possibility, with the quiet fact that we are small and curious and full of impossible questions, and that somehow this makes us beautiful. So, whether your eyes are still open or half closed, whether you're already dreaming or hovering at the edge of sleep, whether you're listening in a city that never rests, or a cabin where the only sound is the rustle of trees, let time cradle you. Let it carry you, not as a passenger in a rush, but as something precious. A thought floating through starlight, a whisper inside the universe. There is no finish line, no destination to reach, just this soft stillness, this quiet now. Sleep not outside of time, but within it. And when you wake, whenever that may be, time will still be there, patient, endless, unfolding gently around you like light through the curtains. Because in the end, the greatest mystery of time isn't where it leads. It's that we are here, in it, together.